So I want to find the inverse Laplace transform of this function. I tried to prove the identity of this generalized result that we're going to see myself, and I came across a couple of errors in my working and thought it was tricky enough and interesting enough to show you guys. So we have C1, a complex number, and P1, a complex number, and S, complex frequency. So when I say C1 star, what I mean is the conjugate of C1. And when I say the conjugate of C1, if C1 is equal to A plus JB, then C1 star is A minus JB. And when we want to inverse Laplace transform something, it's because we have it in the Laplace domain, the complex frequency domain, and we want to get it back into the time domain. Also, keep in mind that when I take the Laplace transform of the whole thing, it's the same as taking the Laplace transform of each fraction. So we use this identity to do the first bit. So if I take the inverse Laplace transform of k of s plus a, you get k e to the minus at. So if I do this on our two fractions, then what we end up getting is some y of t that's equal to c1 e to the power of p1t plus c1 star e to the power of p1 star t. So if we just rewrite that function again, we can see that C1 is a complex number, but we should probably treat it as a polar complex number to make our lives a little easier. Looks like phasor notation. Phasor notation often omits an important little addition, but we won't mention that here. So we're going to treat C1 as the magnitude of C1 multiplied by the angle that it has. We're going to call that phi. So when I say the angle of phi, that little sign, that's the same thing as saying e to the j phi. And in regards to the conjugate, this means that we have the absolute value of C1 with the angle of minus phi, because obviously if it's flipped over the x-axis, the angle is going to be the negative of itself. P1 being a complex number means that obviously P1 star is going to be also a complex number with the opposite sign on the imaginary sign, conjugates. And if we insert all this into our equation for y of t, you can see that I've got the absolute value of C1, e to the j phi, and then I've inserted the value of P1 next to the t, and because it was minus P1, if you remember, it means that the minus sign in the identity is gone. And then we've also got this here, the conjugates involved, so C1 star and P1 star. And obviously if we look back to the equations on the second line, so up here, we can see that C1 star's magnitude is the same as C1. Now just quickly rewriting this and sort of separating the e's, we can see we've got a couple of minuses in the exponents on the right hand side, but none on the left. But we've still got some common factors. So let's pull them out. And now it becomes a little bit more obvious what we've got. If we use Euler's formula, we can now put this into terms of cosines and sines. Notice in the pink that I've taken care of that minus sign on our minus e to the j. I've now put that in here and in here. We're going to use the identity as cosine of negative x is equal to cosine of x, and sine of negative x is equal to negative sine of x. And filling that out, we now get a plus for the cosine, because obviously having a negative on the inside for cosine doesn't matter, and a negative for the j sine, because having a negative on the inside does matter for sine. But I've also used orange boxes to signify these two parts here, which, if you notice, are going to cancel each other out inside the brackets because of the negative of each other. So let's move this up here. But we also have some similarities in the cosines. So if we simplify this down a little more, we're going to get this. And this is the identity that you'll see in your textbook. But at least now you know where it comes from.